So any doubts from last week?
Sir, for peak current mode control,
Mm-hmm.
why the current sensing is preferred to measure in the high side switch?
Okay. Because it is the buck converter, right? So in the buck converter, the high side switch will carry the current when it is rising. That is good. Okay, I will draw and show. Yeah. So, good evening, everyone.
Sir, what is the question, sir?
So the question was why the buck for peak current control, why do we prefer high side current sensing? So do you know why?
Sir, even in a low side switch, it falls from the peak, right?
Yeah.
Then
But,
why not that low side switch?
Okay. So this is my buck converter, right? So this is my buck converter. So my inductor current is like this. Okay. So my current flowing through S is this. This is the current flowing through S. And this is the current flowing through S bar. Okay. This is the current which is flowing through S. And this is the current which is flowing through S bar. So for peak current mode control, we need a maximum peak. Okay, this is my peak. So why we use high side current sensing, why we prefer high side current sensing at switch S is, I will give the set pulse over here. And from the previous value of inductor current, it starts rising, keeps on rising until it reaches the peak and then it switches off and then S turns off. Okay. And then, so the inductor current which was flowing like this, instead it starts flowing like this. So then it starts falling through this switch S bar, it starts falling. So at the low side, it is an after effect. Okay. If we have this peak reference over here, if we are controlling the low side current, it is at the maximum value. It starts at some value, it falls, and then this is the waveform which you will see at the low side switch. Okay. So in this way, we cannot trigger it at the peak value. Okay, we can instead for this we use valley current mode control. At this valley, when it touches the valley, then we turn off the S bar.
Sir, I didn't get the same information which is in the high side switch is available in the low side switch too. The
No,
maximum.
it is available. The maximum value is available, but at what time is that maximum value coming? We don't know, right? See, yes. I just one minute. My control set. So okay. This is a peak. Okay, this is the peak reference I have. In peak current mode control, what do we have? We have a latch. We have a latch that is connected to the reset switch, and we have a set switch. Okay, and this is my tube. So my set comes periodically after a time period of T. Okay. And this is my inductor current, and this is my peak reference current. Okay. So in this waveform, if you see, when the inductor current tries to become more than the peak reference current, then it gives a 1 over here, and then this Q turns 0, because this is a SR latch. Okay, it turns 1, resets, Q becomes 0. So at this instant, you give a set pulse. You give a set pulse periodically after this time. You give a set pulse, you let the current rise, and then when the current reaches the peak, then you reset it, and then Q turns 0. Okay. So when you're doing peak current mode control, you want to have the information of when the current is rising. Current starts at a small value, and it starts rising. And when it reaches the peak value, you want to turn off the switch. So you need to know at what instant the current is touching the peak value. Okay, you don't want to know when the current starts falling from the peak value. You want to know the instant at when it reaches the peak value. So that is why you do high side current sensing. So if I'm sensing high side current sensing, the current which will come over here will be of this form. Okay, so I can compare it with the peak reference value.
Okay, sir.
So this gets interchanged if it becomes a boost converter, because the main switch becomes opposite with that. So those things you must take into account. It's not that high side current sensing is only like for peak current mode control. High side current sensing is required for buck converter, and for boost converter you need low side current sensing. Okay, see, there are
One
three
more
types.
thing.
Okay, yes.
Okay, okay. Please, sir, please continue.
Okay, so this concept of various current sensing techniques will be taken in the next week, I think week 6 or week 7, where various current sensing techniques, various current sensing, whatever equipment or components are used, current sensing techniques will be elaborated. And there also low side current sensing, high side current sensing, full current sensing, all of that has been taught and will be taught. Okay.
Okay. Sir, one more thing.
Yes.
Like for duty ratio less than 0.5, valley current mode control is unstable and there is some concept.
Yes.
Could you please explain it even now or at the end it is fine?
Okay. Yeah. Okay, we'll explain that later. And yeah. So any other queries regarding this one? So I'll proceed. So today the outline of my presentation is we will be touching about the modeling of the switch mode power converters and certain blocks in continuous time and discrete time. We will also be talking of peak current mode control stability. Also, we will discuss how we make the state space model of a DC-DC converter, how to write those matrices for the DC-DC converter, etc. Then how do we make a discrete time large signal model using the state space model? What are the steps and the procedure to make a discrete time large signal model? And then how we will compare. We create a discrete time large signal model and we compare it to the actual switch simulation, and we see how it is matching, how the discrete time large signal model is valid. That we will be discussing. Then we will look into how we will derive the small signal discrete time model from the discrete time large signal model. Okay, and then we will finally do certain questions. So now we will do certain blocks like the PWM modulator, zero order, etc. We will model it. So this is my buck converter. Okay, it's my So this is a buck converter with a high side switch, low side switch, inductor, capacitor, filter NC, and my load. And it has this ESR of the capacitor, the DCR of the inductor, etc. So we make this.
audible, sir.
Sir, your audio is muted.
Okay, now it's clear, right?
Yes, sir. Yes, sir. Clear.
Okay. So this is the AC small signal equivalent model, where it consists of just a linear model and these perturbed
Sir,
quantities.
your screen is not shared.
Achha, achha.
Sir, what's the difference between large signal modeling and small signal modeling?
Okay. So the large signal model is like the behavior of the entire over the entire range of this operation. But the small signal model is like the behavior around a certain neighborhood, around a certain operating point. So the
Sorry,
last,
could you please repeat, sir?
okay, the large signal model is the actual model of the system. Okay, it includes all the dynamics of the model. But the small signal model is a linearized model of the system, which is valid only around a certain operating point. Okay. So let us assume it's my suppose you can see one pen, right? Suppose the behavior of a system is like this. Okay, this is the behavior of a particular system. So this behavior of the system is the large signal behavior. But a small signal model is like we take around this point, we linearize it, and the behavior around this point is linear. Okay. So the model which will represent the behavior in this small region is known as the small signal model. But the model which will represent the entire behavior is known as the large signal model.
Sir,
Yes.
there are in this large signal model, there are several points in which the converter can operate. But if
Okay.
we say a single small signal model,
Mhm.
if you have one unique small signal model, so how can we say it is unique to one particular point?
Yes,
Then
yes.
how can we say in other can understand in other points?
Okay. Usually you are designing your converter, it has particular uh, rated operating mode of operation. Okay. So around that operating point, we will design the small signal model. We will linearize the model and we will use that small signal model for our analysis. And it could be that it will deviate from that actual operating point around which we have, like it. See, we may have designed it for over here, but it might operate over here, etc. So we must, when we are doing, the controller design, etc., we must consider the worst possible scenario, and we must design it accordingly. Where this minimum phase, where we will like where the phase is very less. So the stability margin we'll have to take into consideration while designing a controller. See, we use small signal model because it is linear, and if we want to use linear control techniques to design the controller and to analyze a system, then it is required that we should have a linear model. And our this DC-DC converter is not a linear model; it is a non-linear system. Although it consists of inductor, resistor, capacitor, which are linear, but because of the switching, it is changing from one mode of operation to another mode of operation. Hence, it is a switched linear system and it is a non-linear system because there is a discontinuity. That is why we make the small signal model to represent the averaged behavior of the DC-DC converter. So these concepts have been taught in the previous NPTEL course, and I advise you to go through that. Okay. Any doubts? Please ask. Okay. So this is our small signal model. It has its own, you see, it has its own limitations that it's only valid around a particular operating point, etc. But it gives us insight into the operation of the system, like what happens if my input voltage changes. If my input voltage changes, what is the effect on the output voltage? If my duty ratio changes, what is my effect on the output voltage? If my load current changes, what is the effect on the output voltage, etc. So all these effects we can, we can visualize, we can try to understand what is the cause and the effect using the small signal model. So if you will see this actual buck converter, DC-DC converter is converted into a linear model. There are certain steps and procedures, and this AC equivalent model is used for further analysis. So,
Sir, why it is mentioned AC is equivalent circuit? AC in the sense alternating.
it is like a perturbed quantity. That's why. So when we do these modeling techniques, small signal modeling, etc., when we go for frequency response, right, we are applying an AC perturbation. So probably because of that, that's why they are saying AC equivalent model. Because
Okay.
the DC equivalent model is the steady state equivalent model, which is DC value. Okay, but the AC equivalent model is the, what you say, suppose you just see this is my inductor current. Okay, this is my inductor current. So the average inductor current is this. This is my average inductor current. So this is my DC value of my inductor current. And this ripple, this is my AC component of it. So if you would use an oscilloscope, there are three modes of operation. One is DC plus AC, where it will show like this. Another is AC. Just suppose it is only in AC mode. What we'll do is it will remove this DC component, and that will be at 0, and around 0 it will around 0 around 0 it will show the behavior. So it will remove the DC component and will show the AC component of the signal. Yeah. So basically the AC just signifies the variations and the ripple around the DC steady state value. Okay.
So we consider all the input voltages and currents are varying with respect to a steady state value.
Yeah. Yes. This is just
This circuit.
Okay. Tell.
No, sir. This circuit which you are drawing at the bottom is
Mm-hmm.
it represents the variation of the parameters, variation of all the voltages and currents with
Yes.
respect to steady state in the buck converter.
Yeah. This is the
Is that what
variation.
it represents, sir?
Yes. That's what it represents.
Okay. So that perturbation which we are talking about is originating from this V input.
Which one? Which perturbation?
That small variation we are talking about. That small disturb from the steady state value.
Okay. Yes.
So that variation is originating from this input voltage variation. Is it, sir?
Yes. See,
Is that what the understanding should be?
no. Yes. This is my buck converter. In actual operation, we want the input voltage to be fixed, output voltage to be regulated, and the load also to be fixed. But when it is operating, there could be changes in this. Okay, there could be changes in the load resistance, which results in changes in output current, and those will affect my output voltage. And when they are changed, the duty ratio also changes based on your control. So all those effects are modeled by this. Okay, all those effects are modeled by this. How one change affects the other change. So if we will represent the overall model of the system, it will look like this. Okay, this is my output voltage, and that depends on the changes in the duty ratio, the changes in the output current, and the changes in the input voltage. And this is GVD is my output voltage to my change in duty ratio. Z output is the change in output voltage with change in output current. And this is the change in output voltage with respect to change in input voltage. So this is known as the control to output transfer function, because my D is my duty ratio and my output is my output voltage. So this is the transfer function of GVD. So my GVD is actually V output by S D per term of S. Okay, this is my transfer function for changes in duty ratio to reflecting in changes in output voltage. Similarly, I have a transfer function which shows what is the changes in what changes in input voltage, what is the effect of changes in output voltage. That is known as audio susceptibility. And the next one is the output impedance. That is what changes in my load current result and what is that effect on in the output voltage. So all of those combined effects is the resultant output change in output voltage. Okay.
Sir, here,
Yes.
here while we are calculating this GVD,
Yes.
Change in output voltage with respect to duty ratio.
Mhm.
At that time, we will consider this I naught and V into the 0.
Yes.
Sir?
Yes. Yeah.
But actually, by changing the R, the current changes. But while deriving the output impedance model, there is R and there is a load separate current as a sink is shown.
Yeah. See, there are various ways to represent the load current. See, the output load current could be like a constant power source. It could be just like a constant resistive source. It could behave like a resistive source plus a like a variable current source, etc. Those are the various possibilities. So you're talking about this, right? About this, no?
Yes, sir.
Yes. So in this model, what they are doing, they've kept the resistance fixed, that is there. But this I output represents the changes which happen in the output current and how it affects the other variables.
Okay.
Mhm. So when we find a transfer function, that is what is the transfer function from GVD, control to output transfer function, that is equal to V upon alpha 1 plus S upon omega ESR by delta S. Okay, the alpha is R plus RC upon R. Now my RC is my ESR. RC is my ESR of my capacitor. R is my load resistor, etc. And delta S is my characteristic equation, which we will show later. Similarly, for audio susceptibility, it is given by this formula. The output impedance is given by this formula. And this is the characteristic equation, delta S, which is same for all these three transfer functions. Okay. So further details of these transfer functions, etc., you can find in this lecture 23 for the previous NPTEL course control and tuning method. So these just basically represent, these transfer functions represent what changes occur due to changes in the input voltage or changes in the duty ratio, or changes in the load current. How
Sir,
this is
won't there be small signal modeling in this aspect? Like AC signal equivalent circuit means everything changes, you are saying?
it is, see, the small signal equivalent model represent the overall effect of what changes can happen. Okay, but when we find a transfer function, if you are finding a control to output transfer function, we set the output current perturbation and the input voltage perturbation to 0. And then we find a transfer function.
Okay. Like finding the transfer function means it is the AC like small large signal modeling.
No, it is a small signal model.
Transfer function is also small signal modeling.
Yeah, yeah.
Okay.
So next we proceed with this. So we have a pulse width modulator. So you guys know that for PWM, okay, what do we have? We have plus. So we have here minus, and this is plus. Okay. Okay, change it. Okay, so assume this one. This is my PWM modulator. This is my sawtooth waveform. Okay, and this is my V-com, and this is my VRAM, and this is my output, which is my duty ratio. Okay, so when my V-con is high, this is my V-con. So when V-con is high, this will come out to be high. Okay, it will come out like this. This will be the output Q. This is the pulse width modulator. So if we see it over here, so this is my pulse width modulator, and this is the output. So this is my V-con is varying with time. V-con is varying with time, and at this region it is intersecting it, and this ramp is going above it. So my effective duty ratio will be like this. Okay, this is my effective duty ratio. Because I have V-con, oh, this is plus, this is minus, this is my V-con, and this is my VRAM. Okay. So when my V-con is more than my VRAM, then the output is high, and when V-con becomes less than VRAM, my output is low. And in analog control, my V-con will have a slight variation, slight change. It will not be constant. In digital control, it is constant, but in analog control, it varies. So when this is the scenario, we want to find the transfer function. We want to find the transfer function or the gain. Okay, the effective gain of this modulator block. So that is represented using this. So my V-con divided by my VM, that is my time. Okay, this is a triangle. Okay, this is a triangle. By equality of triangles, we have V-con by B analog TS is equal to VM upon TS. So we cut TS. So my D analog will be equal to V-con divided by VM. Any doubts on this?
No.
Okay. So that is my my gain for analog control. Now, when I will proceed for digital control. what is the difference in digital control is this is how my beacon is changing with time. But when I use digital control, I sample it. So I take the sample at this instant. I take the sample at this instant and it is kept fixed. So because it is kept fixed, my so the meeting ended.
No, sir, no. It is showing that there are 6.5 minutes remaining.
Oh, okay, okay. So I think my network was poor. Okay. Sorry. So my screen is visible.
Yes, sir, it is visible.
Sure. So this is my beacon for digital, and this is my how my VC varies with analog. So when we will compare my duty ratio, which is effectively generated for digital control and for analog control, they are different. But we do not want that to happen. We want the duty ratio which is generated from the analog control as well as from the digital control to be the same. So how should we model it such that the effective duty ratio remains the same when we apply the same input? So what do we do is we will phase shift it. So this is my actual, let me put point. This is the ramp signal, which was the earlier ramp signal. And this is my analog VCon, and this is my digital VCon. So what we do, initially we're taking the sample at the start of the ramp. Now what, in order for the duty ratio which is generated by analog control to be same as the generated with digital control, what is required of us is that we have to shift this ramp signal by this duration d analog ts. We must delay this ramp signal by this duration d analog ts. And if we do that, then the effective duty ratio which we get using analog control as well as the one which you get using digital control will remain the same.
Sir, does it mean like the sampling is also delayed?
No, this is not about the sampling. This is about the modeling. How we are modeling the digital PWM and analog PWM. Or we are comparing the modeling of digital PWM and analog PWM. Okay. So effectively, when we do this, our duty ratio D digital, which we get, that will be equal to e raised to minus this D analog into TS into S into 1 upon Vm. Okay, Vcon upon Vm. So this is equal to Vcon upon Vm. So this is the one in analog domain, and then we just get an additional delay in digital domain. Okay. Any doubts in this?
No, sir, no doubt.
Okay. So now this is my small signal block diagram. Under digital control, this will be my small signal block diagram. So we have a reference perturbation and my sampled value of my output voltage. That is given over here, and that generates my digital VL. That goes to my digital controller followed by a zero order hole, and that will generate VZ perturb which goes to my PWM modulator, and we add this delay. Okay, this delay. So this delay is both the ADC delay and the digital pulse width modulation delay. So both those delays we combine into this delay tau d. Okay, both those delays we combine into this delay tau d, and that generates my effective duty ratio, and that effective perturbation duty ratio is given to GVD, and that generates a change in the output to V output prime, V output perturb. Okay, that is sensed by my feedback gain H, and then that is sampled using this sampling system. And that sampling is occurring at a uniform time period of T. Okay.
Sir, a zero order hold is used for like sampling and holding. Like, does it mean ADC or DAC, sir?
Yeah, it is acting as DAC. Because this is a digital quantity and this is an analog quantity.
Okay. Then sampling means only like just sampling. Does it means analog to digital?
Yeah, analog to
Just
digital.
sampling.
Yes, yes.
The bottom it is analog to digital, right?
Yeah, yeah.
The bottom one.
Yes. Yeah, it is
Okay.
analog to digital.
Okay, sir. Okay. Continue.
Now, how do we model this zero order hold block? Okay, how do we model it? If so, this is the input. Okay, the input is one sample value, and that is held constant by my zero order hold block for this duration. For this period T, my zero order hold block will hold this value firm, fixed till this duration. This is how my zero order hold works.
Sir, the time period will be decided by whom?
No, this is not a time. It is not always the time period. It is just the delay which we have given. For how long my zero order hold will hold that value which it comes at its input.
Okay. For a finite amount of time, it will hold the same value if we
Yeah.
don't trigger it, right?
Yes. Okay.
Okay.
So this okay. Fine. So this value over here, this is just an impulse. Okay. This is just an impulse which we have given BC per term. This is an impulse of magnitude A. But when I give this impulse, delayed impulse, I get a output VZ prime, which is a square wave like this. Okay, it's a square wave like this. This not square wave, it is just a square over here. Is it audible now?
Sir, audible, sir, audible.
Okay. So this wave can be represented as, how do we represent it as, there is one unit step starting at this point T minus KT, and there's another unit step starting at this point T minus K plus 1 T. So when you, okay, let me draw here. This is one unit step and this is another unit step. Okay. This is U T minus KT. This is U of T minus K plus 1 T. Okay. When we subtract them, we will get this signal. So effectively, this signal can be represented as this signal minus this signal. So that is why Vz per term is equal to A into U of T minus KT minus U of T minus K plus 1 T. Okay.
Okay, sir.
So my input, if I take the Laplace transform of it, it is just A. When I take the Laplace transform of this, if I take the Laplace transform of this, it will be A raised to E minus ST minus E raised to minus ST t plus 1 divided by s. So that will be equal to a into e raised to minus s t upon s into 1 minus e raised to minus s t. Okay, clear. To 1 minus e raised to minus s t. The issue over here, this is my VC prime, VC per term. When I do VC per term of s, this is wrong. Okay, this will not be a, it will just be equal to a into e raised to minus s t.
Sir, VC perturb in the sense large
Okay.
signal or very small disturbance?
It is a small disturbance. Right? So this actually a mistake. Okay. So this is the this is my impulse, right? When I take the VC prime of s, it will be a raised to e raised to minus s k t, and when I do VZ tilde of s, it will be a into e raised to minus s k t upon s minus e raised to minus s k plus 1 t upon s. So that will be equal to a upon s into e raised to minus s k t into 1 minus e raised to minus s t. So when I want to find the transfer function, I have to vz tilde upon s by vc tilde upon s. So that will be equal to a e raised to minus s k t into 1 minus e raised to minus s t upon s divided by a into e raised to minus s k t. So this and this get cancelled. So the effective transfer function is 1 minus e raised to minus s t upon s. So this is how we find the transfer function of the zero order whole block. Yeah.
Okay, sir.
So now so this is my yes.
Sir, before that zero order block, before that the discussion of the zero order block, what have you discussed, sir? I lost the connection midway. Before that zero order block discussion.
Achha. We just discussed about the PWM modulator. How do we get that
Yes, we have.
transfer function that we discussed?
Yeah.
Okay.
Yeah.
So this is the approximate continuous time small signal model which we get using digital control. So this is in continuous time. The digital components are also modeled in the analog domain, and we are finding the effective transfer functions, and then we can get the loop transfer function. So we get k loop is k loop analog s into e raised to minus s tau d. So this, and this all are present in my analog loop as well. But this is the extra thing which has been added in the digital loop. We are getting an extra delay with the digital loop. So this delay gets introduced, and this delay is due to my ADC conversion time as well as my delay due to my digital pulse width modulator, which is given over here. And for further details, you can refer to this lecture. So now we will proceed with the stability, with the current mode control stability conditions. Why duty ratio at duty ratio greater than 0.5, peak current mode control is unstable. Okay.
Sir, wherever if you want to convert the analog gain to digital gain, we have to multiply with the delay.
Yeah, you have to multiply with the delay. Yes. Yeah.
So wherever if you want to transfer the gain from analog to digital domain, we have to multiply with the delay.
We are finding the loop gain. Okay, in this case, it is the loop gain.
Yeah.
Yeah. Based on that, then we can say that. So that loop gain consists of both delays. And this loop gain will be used for designing our controller. Okay. So this is the waveform for mixed signal peak control. We want to discuss about the stability of it. It is fixed frequency. The frequency is fixed, and the reference, and this is virtually an analog to it because the current loop is analog because it is mixed signal. In mixed signal, my voltage loop is digital, but my current loop is analog. And because it is analog, my reference value is fixed. Okay, my reference value is fixed. So what happens? This IL of n plus m1 into dt. So this is a line. So this line I reference of n, this is y, is equal to c, that is the y-intercept, plus the slope m1 into x. Okay, this comes with the form of the equation of a line, y equal to mx plus c. This is my first equation. I reference of n is IL of n plus m1 into dt. Then similarly, my IL of n plus 1 is what? It is just this I reference of n, this value, and then I reduce it by this value minus, I know the slope and the time. So it is minus of m2 into t minus dt. Okay. So then what do? We substitute the value of I reference of n over here. So we get IL of n plus 1 is equal to IL of n plus m1 into dt minus m2 into 1 minus d into t. So this is my equation. And we can even further write it in this form. Now, what we want to do is we want to write this equation not in terms of d. We do not want this variable d because this variable d changes. We want it to be in the form of I reference and IL. So what do? dt over here is equal to I reference of n minus IL of n divided by m1. So this dt value we substitute over here. So when we substitute, we will get the equation to be of this form. So any queries in this part? Hello.
Sir, here we are actually finding the inductor current of the next sample from all the information of the current sample.
We are just analyzing the waveform. Okay. Yeah. We are also getting the equation for the inductor current in the next sample, from the previous sample, and from the slope information which we have, and with the reference information. So if we further proceed with it, we can write it in this form. And then what do? We can even perturb it. So this is my large signal equation. Okay, this is my large signal equation of my current flow. Now I want to find the stability. So I will go to the small signal part. So what I will do, I will perturb it. If I perturb it, I will, what and all I can perturb, I assume M1, M2 to be fixed. Okay. T is also fixed because it is fixed time period. So what can be changed? This can change and this can change. So my effective change over here is equal to IL perturb of N plus M1 plus M2 divided by M1 into I reference of N perturb minus IL perturb of N. Okay, this is the equation, and this minus M2 into T, when I perturb it, that is make any change, it is 0. Okay, because it is a fixed value, right?
What's that?
This M2 into T is a fixed value. We assume it to stay fixed because we assume when we are analyzing it, the M1, M2 are fixed. and T also is fixed. Okay, so this quantity is fixed, so it gets ignored. The derivative of that is 0. So then now this is my perturbed quantity. Now we can take the Z transform of it. If we take the Z transform of it, this will be Z into IL perturb of Z equal to IL perturb of Z plus M1 plus M2 divided by M1 into IRF perturb of Z minus IL perturb of Z. Okay. So I take all the components of IL perturb of Z to one side. I will get IL perturb of Z is equal to Z minus 1 plus M1 plus M2 upon M1 is equal to M1 plus M2 upon M1 into IL reference of perturb of Z. So this becomes IL perturb of Z minus M1 plus M1 plus M2 upon M1. So that comes to the form of IL perturb of Z upon IRF perturb of Z. This M1 plus M2 upon M1, let us assume it to be a constant, that is A assume. So that A divided by Z plus M2 upon M1. Now we know for digital control systems, the pole, okay, should lie within the unit circle. This pole, this is my unit circle, suppose. It is not correct actually. Assume this is my unit circle. My pole should lie within it. It should be somewhere here. It should not be outside. So if that is the case, then my mod M2 upon M1 should be less than 0. And if we substitute that, then we will get my duty ratio should be less than 0.5 for it to be stable.
Could you please explain that last three steps once?
For the digital control stability,
No, sir. Like you are saying, IL by I reference is equal to Z plus M2 by M1.
Mhm.
Is it like Z into 1 plus M2 by 1 M1?
Is it like?
Z into 1 plus M2 by M1?
No, it is Z plus M2 by M1.
Okay. Then, like, how you are saying that less than 0, that point, please repeat once. From unit circle to this point.
Okay. So let us go to the next. Here. So this is my unit circle. Okay. This is my unit circle. My pole will lie somewhere here. It should lie somewhere here. It should not lie somewhere outside. This is my distance of the pole from the origin. Okay. So my pole will be
Okay.
located Z equal to minus M2 upon M1. Okay. So if M2 and M1 both are positive, then my pole will be in the negative side. So it will be somewhere around here. And this would be where my pole is located. Now, if M2 is greater than M1, then Z, where this pole is, this is, okay, this is minus 1 comma 0, this is 1 comma 0. This is 0 comma 1, this is 0 comma minus 1. Okay. Any doubts in this context of the unit
No.
circle? So
No.
if my pole is located at M2 upon M1, minus of M2 upon M1. Okay. So if M2 becomes greater than M1, then my pole will go outside the unit circle. It will come up over here, which will make the system unstable. So my requirement is M2 should be less than M1. Okay. At
Okay.
the border condition, M2 will be equal to M1 and my pole will be at Z equal to -1, it will be over here. If M2 becomes greater than M1,
Okay.
then go further in this direction.
Okay.
So accordingly,
How you are getting 0.5?
getting 0.5 I can get. Okay, oh, how are we getting duty ratio 0.5? Okay, so we
Yes, sir.
want M2 upon M1 to be less than 1, right? Okay. So for a buck converter, this M1 is equal to Vin minus V output. And for
Okay.
one is V output less than 1. Okay, so V input minus V output is less than V output. So V input is less than 2 V output. And my duty ratio, so half is less than V output upon V in, which is my duty ratio. Okay.
Okay, sir. Okay.
Yeah. So this is how we get duty ratio should be less than 0.5. So if you, as you were asking me for valley current control, okay, in valley current control, my reference will be over here. Okay, then I have to draw from here IL of n to this point, and from this point to IL of n plus 1. And if you do that, and then you will find the condition is the opposite. That is, if duty ratio is greater than 0.5, then it is stable.
Greater than 0.5, it is stable. Like,
For valley current,
okay.
Sir, here it seems to be V0 by Vn minus V0.
where?
M2 by M1.
Mm-hmm.
This M2 should be V0 and M1 should be Vn minus V0.
M1 should be
For
buck converter, right?
the slope, yeah,
Uh,
the slope, the first slope should be M1 should be Vn minus V0 by L.
M1 should be V minus V0, right? That is fine. M2 is
Yeah, so it should come V0 by Vn minus V0 should be less than.
okay. Let me export the condition. What is the final thing which will M2 upon M1? Okay. So M2 upon M1 should be less than 1. So it will be opposite. V output upon Vn minus V output is less than 1. So I get V output is less than Vn minus V output. 2V output is less than Vn. So V output upon Vn should be less than half. This is the duty ratio. Yeah, so my duty ratio should be less than half. I don't know, that time I think I made a sign mistake.
This instead of for M2 we have substituted M1.
Yes. Yeah. Okay. So for value control, you have to do the same thing, but just the reference will be at the value point instead of the peak point. Okay, that you can do.
Sir, there is also saying like that for a low duty ratio, we can't capture. There will be noise for the
Yeah.
on time.
Yes.
Could you please for
Okay. So yeah. I'll just get rid of these things. Yeah. So in peak current mode control, okay, this is my IL. This is okay. This is my IL. This is my I reference. Okay, and this goes to my reset switch, and this goes to my set switch, and this is my gate signal. Okay, my set switch comes at periodic events. Okay, which is comes over here. One set signal will come, and the set signal will come over here. In case the duty ratio is very small, okay, the duty ratio is very small, like this. This is my duty ratio. The duty ratio is very small. My inductor current will be like this, and it will fall like this. It will be like this, and it will fall like this. Okay, so in this case, my duty ratio is less than 0.5, and then I can apply peak current mode control. But if this was the case, if duty ratio is less than 0.5, I cannot apply valley current. Okay, you were asking a question about noise, right? About very low duty ratio, right?
Yes, sir. Like for less than 0.5, how we can, like you are saying, for less than 0.5 duty ratio, we can't apply peak current mode control.
No. I am saying for duty ratio less than 0.5, we can apply peak current mode control.
How, sir? Like here, the time is very less, and within that short time, there will be noise at the starting point and at the peak point.
Noise will be
First
only
cycle.
noise will be only over here, right? Noise will be only over here. Here also, after it reaches the reference, then there will be noise. So that noise will come over here. It will get reflected over here. But that is why we use a SR net. So even though there is noise, at the first reset, it will turn off. The switch will turn off. So what your doubt is, if it is reset is suppose this is my
No, sir. Actually, my doubt is if duty ratio is less than 0.5, then which is feasible and which control is feasible and which control is not feasible and why?
Okay, if duty ratio is less than 0.5, peak current mode control is feasible. Because it has been proved in the derivation which we did earlier that when duty ratio is less than 0.5, peak current mode control loop is stable.
Yes, sir. From that it is okay. Can't we explain it intuitively, sir?
Intuitively, it's like this is a mathematical derivation actually. So
yes, sir.
that
Like
is-
in the lectures, sir has mentioned that for that on time we can't like I didn't get that point from him. That's the thing I'm asking you.
Okay.
Actually, it is in lecture 15 and in lecture 20.
Lecture 15 and lecture 20. Yes. So when the duty ratio is very, very low, okay, then it is preferred to go for valley current mode control. Why? Of course, in this, it is short duration. This is a short duration, right? So in this small short duration, there will be lots of spikes. There will be spikes over here, and that spike might still propagate over here. So if that is the case, then we should go for valley current mode control. But the problem with valley current mode control is it is unstable for duty ratio less than 0.5. So what do? Is we go for constant on-time control in that case. Constant on-time control, what I can do, I can give this constant on-time control to be very small. This is from a timer. It is not generated by this latch circuit. It is generated by a timer. So I can set the timer to be as small as possible. And then it will be off as per the loop. Then it will be on for a very short duration and it will be off as per the loop. So in this case, my duty ratio, effective duty ratio can be less than 0.5. But it has been proved that for constant on-time control, it is stable. The current loop is stable, even though the duty ratio is less than 0.5. It is stable throughout. For duty ratio from 0 to 1. It has inherent current loop stability.
But here we are saying that it is like it is stable for less than 0.5. How can we correlate these two, sir?
Okay, yes. So in this case, we have not considered the noise which could happen. Okay, there could be certain noise which could happen. So what happened is I give the set pulse over here. Okay, I give the set pulse. If I give the set pulse, what happens? My switch should turn on. It should turn on, and then when the reset, once the reset pulse comes, it should turn off. But what if the set pulse comes at the same time and the reset pulse also comes at the same time? Then the switch will not turn on only; it will continue remaining off, and that will result in the voltage dipping, fully dipping. So to prevent that, what do we have is once we give the set pulse. Okay, once I give the set pulse, what happens? When I give the set pulse over here, assume I give the set pulse, there will be spikes. Okay, there will be certain spikes. Suppose by chance that spike is so large. If that spike is so large, what will it do is it will make reset high and it will turn off the switch. It will turn off the switch. So it has turned on very quickly, it turns off. Okay. That is how it would happen because of the spike. Now we do not know that this operation is happening because of the spike or it is happening because my reference is very low. If the reference was very low, suppose over here, or suppose over here, if my reference was very low, it would reach this value and it would reset. Okay. But we don't know whether it is because the reference is very low or because there's been a spike. And that spike will result in spurious turn off, which is not as designed by or as intended by my closed loop. So to avoid that issue, what do we do is, after we give the set pulse, for some duration. This is known as the blanking period. Okay, this is known as the blanking period. In this blanking period, any reset high signal which comes, we will ignore that. We will ignore any reset signal which comes over here, so that the switch will be on at least for this minimum duration. Okay. So you want me to repeat because it is a very complicated thing. Or shall I proceed?
At the end, you are saying that for duty ratio less than 0.5 and if it is the current mode control, we should go for constant on time.
No. I'm saying for duty, not duty ratio less than 0.5. I'm saying for duty ratio like around 0.05. A very low duty ratio.
Yes, very low duty ratio.
Very low duty ratio. Very low duty ratio, it is not possible to go. Because in that small instant, I am giving a blanking. If my blanking is given, if there's a blanking period, assume that this is my blanking period and this is my time duration. Okay. Like, let me just write in figurative value. Assume my time period is 1 second. Okay. My blanking duration is, assume it to be 0.02 second. Okay. So I give my set pulse over here and my switch will be on at least for 0.02 second. So the minimum duty ratio which I can get will be 0.02. Okay, minimum duty ratio which I get is 0.02. But suppose I want duty ratio even less than that, that is not feasible because I have to provide in my practical setup, I need to provide this blanking. And this blanking duration will be of some particular value. So I cannot get a duty ratio which is less than this value. Which is less than this value. So this is the limitation using this setup.
Okay.
So now if
in that case, we have to go for constant on time.
in that case, we have to go for constant on time. If there was no noise, no problem, or no issue of these noise is like not considered in this derivation. Because noise is something we do not know. Noise changes, it is random. Okay. So to avoid that noise, we have to have in our hardware setup, we have to have a blanking period. Okay. And that blanking period should be of some considerable value, some considerable time duration. Okay, and that considerable time duration is what limits the minimum duty ratio which I can practically generate using peak current mode control. Okay. So any other issues? You can remind me, I can attach one good document regarding that. Just note down.
What's it?
The peak current mode control, the blanking period, or I can add that reference also. Peak current mode control, blanking. Okay, I'll in the YouTube video I will add the link for the blanking reference. Okay, why that minimum blank that is there.
Okay, sir. Okay, sure.
So I'll proceed further. Actually, we have lots to cover. So so this is for this. Even similarly for fully digital current mode control, also you can get these difference equations, you can write them and you can derive it. And it has been shown that there is a slope requirement. My slope for my emulated ramp. So in fully digital current mode control, what happens? I am taking the sample of the inductor current of the previous cycle. I'm using that previous cycle value and I'm generating my ramp signal, okay, my emulated current signal. So when we incorporate the effect of the delay, one cycle delay, and we write those equations and then we derive this transfer function, it is found that this slope MC should be greater than M1 plus M2. Okay. So if we use such a slope in my digital platform to implement this emulated ramp, then my current loop will be stable. Okay, so this meeting will end in 1 minute. Then after the meeting ends, I will again restart the meeting. All right. So we have analytically proved that if this slope is used for generating the emulated ramp, then my current loop will be stable for fully digital peak current mode control. Okay, so we will proceed further. Now we will consider state space modeling. Okay, this is my synchronous buck converter, and I want to generate the state space model. So when I want to generate the state space model, I need to select particular states. Those states we have selected, it is usually selected to be the inductor current IL and the capacitor voltage because they vary continuously. There are no discrete changes. Okay, it is a continuously varying, and so this differentiable. So these are the states which are selected. Next, my input variables are my input voltage and my output sync current. So the sync current is a little bit more advanced topic, and so we will ignore that in our derivations. Okay. So what we will do is, so this is a buck converter. Okay. It has two modes. This buck converter has two modes. In one mode, S is on, that is Q equal to 1. One mode is Q equal to 1. When Q is equal to 1, this switch is closed and this switch is open, and it will have one sort of, this will be my, it is open. This is my inductor L. This is my capacitor. Let us just ignore some resistor. And this is my resistor. Okay. This is my model of the buck converter when Q is equal to 1. When Q is equal to 0, it will be like this. It will just be my R2, my L, my RL, my RC, my C, the capacitor, and the resistor. This is when Q equal to 0. So when Q is equal to 1, we have this circuit, and when Q equal to 0, we have this circuit. So there are two different circuits, and the circuit is determined based on the switch, which switch is on. So when there are two different circuits, we get two different state space models. We get two different matrices. So the state space model is, that is x dot derivative is equal to AQ into x plus BQ into U. For buck converter, it is given in this form. Okay. So if you want to refer to details, you can find it, how it is generated, but it is of this form. So we are getting it to be like this. My x dot is equal to AQX plus BQ into U. So if my Q is equal to 1, I will have x dot is equal to A1 into X plus B1 into U. If my Q equal to 0, my differential equation will be x dot equal to A2X plus B2 into U. So if I put Q equal to 1 or 0, my A matrix remains the same. My A1 and A2 is equal to A. Okay, because in this AQ matrix, there is no term Q present over here. But in my B matrix, there's this term Q present. So it will change. So when Q equal to 1, my B1 will be 1 by L 0 alpha RC upon L minus alpha upon C. But when Q equal to 0, it will be B2, which will be equal to 0, 0 alpha RC upon L minus alpha upon C. So any doubts in this? Because this is the basic foundation. Or I can proceed further. Okay, this is taught in the previous NPTEL course, but also I've just given a brief input. So we are representing the derivative of these states in terms of a matrix into the states plus another matrix into the input. You guys would have learned this in control systems, okay, in your bachelor's. So now when we find the solution of that state space vector, it will come off in this form. X of t is equal to e raised to aq t minus t0 into x of t0. X of t is t0. Sorry. So t0 is my initial time instant. T0 is my initial time. X of t0 is my value, the value at this initial time. X of t0 is the value of this initial time. So this, suppose this is my state, it is varying like this. This is my x of t0 and this is my value at x of t. So this behavior is determined by this equation, e raised to aq t minus t0 into x of t0 plus integration t0 to t e raised to aq t minus tau into bq into u of tau into d tau. So if you see, this part is depends on the initial state. This part depends on the initial state and does not depend on the control input u. But this part depends on the input and does not depend on my input signal. This part depends on my input and does not depend on my initial condition, initial state. So this is known as my zero input response and this is known as my zero state response. So the response, the dynamic response of the system consists of two parts, two components. One is my zero input response and one is due to my zero state response. Okay. So that is given by this equation. Now we will assume that the input voltage and the output current are constant. Okay, and this is, the assumption is valid. Just this assumption is valid within a switching cycle. Because the switching cycle is like this in this small duration, which later let us assume the time is around 10 microsecond. Okay, this corresponds to switching frequency of 100 kilohertz. So in this time, my input voltage will change very minimum, very minute value. So this approximation that the input voltage and the output current don't change is a valid approach. It's like we can use. It is an engineering approximation that is well observed and it is believed in. Okay. Then what is the problem is, so what we say, this my input does not change. If I assume my input does not change, this is fixed and this is fixed. So what I have to do is I just have to integrate this term. So when I integrate this term, the solution comes out to be of this format. And this is only applicable when this matrix is invertible. It is invertible. If it is not invertible, then there's a different method which is not required for you guys to know. That is a higher research topic.
So please repeat once, like above assumption is perfectly valid within a switching cycle, that point. And u of t is said to be u, that thing all one.
Okay, okay. So in this short duration of 10 microseconds, okay, practically my input voltage will not change. Okay, though my input voltage may have some certain fluctuations, but I can approximate it to be at a fixed value throughout the switching cycle. Okay, similar. So if it is a fixed value, if u of tau is fixed value, during this integration is happening for a small time instant within or about the time period. Okay, so if it is a very small instant where I can substitute the approximation that my my input is not changing and it is a constant value, so u of tau I substitute as u, and bq also is fixed, bq also is not changing. So bq into u is fixed. So what happens is this term is a constant term. So this constant term can come out of my integral. Okay, this constant term can come out of my integral. And the only thing which I have to integrate is this term. And when I integrate this term, the entire, what I will get is this equation. This is the equation I will get. Okay.
Sir, like after integration, we get t minus t naught and the,
Yeah, yeah, t minus t naught we get, yes.
but where is that?
What term?
You said BQ and U are constant, you have taken it out.
Yes, yes.
Then we have E into AQ, E power of AQ, T minus tau, integration
And
for
this is
that
t
thing.
tau. So that's why this tau term goes away and it is replaced by t0. So if you,
Sorry, sir, could you please repeat it once?
it is integrating it with respect to tau, integrating with respect to tau. And when you
Okay.
substitute these final values, t0 and initial value and final value, you will get it in this form. Okay. Yes. So now,
Sir, how this BQ is constant because of U?
okay, so this, okay, so we will assume either the switch is on, or it is off. Okay. When the switch is on, I have B1 and I have B2. Okay. So this integration which I am doing is only when the switch is on or when the switch is off. So if I assume in this instant when I'm doing integration, my B1 is fixed. So I can put B1 as fixed. U also is fixed. So then this assumption is valid. I am not saying that B1 is fixed throughout the switching cycle. I am saying that the input voltage and output current are fixed within the switching cycle. And when I'm integrating it, I will know it is in which mode of operation, whether my switch is on or whether my switch is off. And if it is on, then I will take P1 matrix. If it is off, I will take my B2 matrix and I will proceed.
Sir, here the time instant T0 to T is either in on mode or in off mode.
Yes. That is T0 is my initial condition and T is my final condition. That has to be either in the on mode or in the off mode. Yeah.
Okay. Okay, sir.
Okay. So this is the basic of how I'm going to derive the discrete time model. Why I do not use the continuous time model is because the small signal model, it does some sort of averaging and so much of real information is lost. While that information is retained by the discrete time model. Because in the discrete time model, I'm actually considering how my inductor current is varying within the time period. Whereas in my continuous time small signal model, I'm averaging out that variation and I'm just seeing the average value. So this has certain analytical capabilities more powerful than the continuous time model. So that is why we are studying it in detail. So what we assume is, so for buck converter, we will assume it to be an ideal buck converter. Okay, I will use an ideal buck converter. These are very, very complex.
Hello.
Yes, yes.
8:45 కి స్టార్ట్ అవుతా అన్నాడు.
Sorry. Okay.
ఓకే, మీరు ఇంకా స్టార్ట్ అవ్వండి.
So we'll consider an ideal buck converter. If it is an ideal buck converter, what will happen is RE will be equal to 0. Okay, RC will also be equal to 0. Alpha also will be equal to 0. So this is a standard thing. This is how it works. For an ideal buck converter, I assume that there are no parasitic drops. there's no parasitic resistance, etc. I am using this assumption so that it will become easy for me to derive the results. The results will not be as accurate when I consider all the parasitics, but using this ideal equations, I will get insight into the behavior of the system. Okay. So if I use these values, what I will get A1 to be equal to 0, 0, 0. No. It will be RE upon L 0, 0, 0. No, this is not possible. No, my alpha will be equal to 1. My alpha will be equal to 1. So I will get RE, just let me rub it off. Okay. My alpha will be equal to 1. So I will get it to be minus some RE plus RC. Okay, RC is 0 and RE also is 0. So this will be 0, 0. This will be minus 1 by L. This will be 1 by C, and this will be minus 1 upon RC. This is my matrix A1. And this is the same as A2. Okay. Next, I will ignore these. These two are due to my output current. I output sink current, which I will ignore. Okay, I will just assume that my load is purely a resistive load. So what I will get is B1 is equal to 1 upon L 0 and B2 is equal to 0, 0. Okay, this is what I will get. So any issues in this? So I'll proceed further.
Sir, why we are ignoring the second column of B?
Because it is relating to the current sink. Now I assume the current sink, I ignore that effect. Okay, I ignore it. I don't want to include that effect of current sink in my analysis. I will assume that my load is fully resistive so that it will make my analysis easy. Okay.
Sir, alpha is the ratio of resistance.
Yeah, alpha is actually alpha is equal to R upon R plus RC. So if I set RC to be equal to 0, then alpha will come out to be 1. So yeah, proceed. So this is my discrete-time model. How I will do it is I will start with some initial conditions, say around here xn. Okay, suppose this is my initial condition xn. Okay, then what will it be? It will go on, the switch is on. So I will consider these matrices A1, B1. I will use these matrices A1, B1, and I will use the equation for the state space solution, and I will find the value at this point. Okay, at this point, let me name it as x1. Okay, at this point, let me name it as x1. Then from x1, I will use the equations matrices A2, B2, and I will find out what will be the value at xn plus 1. So this is my discrete time model. From xn, I will go to x1. From x1, I will go to xn plus 1. Then I will write x1 in terms of xn, and effectively I will write xn plus 1 in terms of xn. So I will describe that in further things. Okay. So I will get a sort of discrete time map. Okay, those are complex terms. Okay. So what happens in this? We will consider trailing edge pulse width modulation. Okay, I'm considering trailing edge pulse width modulation. This is my switching period set pulse when my switch turns on. When it is on, it is mode 1 operation, M1. When it is off, it is mode 2 of operation. Okay, when it is M1, the matrices are A1, B1. When it is M2, the matrices for the circuit is A2, B2. Okay, so I take the sample slightly with the delay, considering the delay which we have discussed in B2. I take the sample at delay TS. I take the sample over here. Okay, after I take that sample, it is still in mode M2. It is still in the off mode. Okay, so this is my X xn. From xn, it will reach x1 where mode 2 finishes. Then from mode 2, it will go to mode 1, and till the end of mode 2, I will denote it as x2. Then this x2 will evolve to come to xn plus 1 when it is in mode m2. Okay. So at t equal to nt, my state is xn. At t is equal to nt plus ts, my state is x1. Okay, over here. And then at t, which is equal to nt plus ts plus t on, this is my on time, and nt plus ts plus t on, so that is at this instant, this is my x2. Then at the end, at n plus 1 t at this time, this is my xn plus 1. So this is how my state is evolving in time, and it is in either mode 2 or in mode 1, etc. And this is how I represent the state evolution over the entire switching cycle. Okay. So now we'll proceed further. So what I will do is, it is in mode M2. Okay, this is okay. So this is just repeating from this duration to this duration, it is in mode M2. From this duration to this duration, it is in mode M1. Then further from this duration to this duration, it is again in mode M2. All right. So this is how my state, this is my state X n assume. This considers my inductor, what is the value, as well as my capacitor, what was the value of the capacitor voltage. That is included in my state vector, right? So now it goes from this. Okay, this is again a repeat. So what I will do is, my x, this is the equation. What we have is, we know the equation is x of t is equal to e raised to a q t minus t0 into x of t0 plus e raised to a q t minus t0 minus I into a q inverse into bq into u. This was the state space solution which I had shown in the previous earlier slide. Now for this duration, for nt going from where t lies between nt to nt plus ts, my initial state vector is xn, my final state vector is x1. My matrices are a2 is equal to a and b2 is equal to 0. So what I will get is my x of 1, that is my final state, is equal to e raised to aq is a2 is equal to a. So e raised to a. Now t is the final time, that is nt plus ts, minus t0 is the initial time, that is nt. So it will be nt plus ts minus nt. And x of t0 is equal to xn. So this is how I get it there. Then that will be equal to e raised to a into nt plus ts minus nt minus of I. This is a unit, this is the identity matrix, into a inverse, aq is a, bq is 0, so I get it as 0 into u. So what I will get is x1 is equal to e raised to a into nt, and nt get cancelled, e raised to a into ts into xn plus 0. This is how I'm representing the state vector x1 in terms of xn. Right? So any queries in this? Okay, so now I will proceed to the next thing, and hopefully I'll again do it in the next thing, and hopefully that will help you to understand it further. So this part I have shown, it is for this mode. Okay, for this time, when the state is evolving from this time xn to x1. Okay, and I have substituted those values in this equation and I get it to be of this form. Now I will go to the next mode. Now I will look into mode M1 when it is on, when the switch is on. When the switch is on, the matrices are A1 and B1. Okay, those are my on matrices. So now I will go to the next state. Okay, in the next one, again, I will have x of t is equal to e raised to a q t minus t0 into x of t0 plus e raised to a q t minus t0 minus I into aq inverse bq into u. Now I will substitute the value here. T is what? Here T is NT plus TS plus T on, and here T0 is equal to NT plus TS. So T minus T0 is effectively T on. Here my AQ is equal to A and my BQ is equal to B1. Okay, so I will get, and my X of T is equal to X2 and my X of T0 is equal to X1. So I will get x2 is equal to e raised to a t on into x of 1 plus e raised to a t on minus I into a inverse of v1 into v in. Okay, this is how I get, because my u is actually v in. So this is how I represent x2 in terms of x1. Now what I will do is, I will represent x2 in terms of xn. I got in the previous time, I got x1 is equal to e raised to a ts into xn. So I will substitute that in this equation. I will get x2 is equal to e raised to a t on into e raised to a ts into xn plus e raised to a t on, this doesn't change, e raised to a t on minus I into a inverse v1 into vn. Okay, so this is my equation 2, this is my equation 1. So now I will proceed further. I will go to the third and final time in this duration. So in this duration, what is happening? Again, I will just write x of t is equal to e raised to aq t minus t0 into x of t0 plus e raised to aq t minus t0 minus I into aq inverse bq into v in. So I will substitute those values. Now x of t in this case is equal to x of n plus 1 and x of t0 is equal to x2, and my t minus t0 comes out to be it will be n plus 1 into t minus nt minus ts minus t, that will be equal to t minus ts minus t. So when I substitute the values, we get x of n plus 1 is equal to e raised to a into t minus ts minus t on into x of 2 plus e raised to a t minus ts minus t on minus I into a inverse of, okay, here again v2 is equal to 0, v2 into vn. So that will give me x of n plus 1 is equal to e raised to a t minus ts minus t on into x2 plus 0. Okay. Any confusion in this? So now what I will do is, I got x2 over here in terms of xn. I will substitute that value over here. And the final equation which I will get is given by x of n plus 1 is equal to e raised to a t into x of n plus e raised to a. So what's my equation which I will get plus e raised to a t minus ts minus e raised to a t minus ts minus d into t a inverse v1 into vn. Okay, this is my final equation. So this effectively how it looks like x of n plus 1 is a function of x of n comma d comma vn. Okay, so this is known as the discrete time map. So this is the complete discrete time map which we get. Xn plus 1 is equal to e raised to at into xn plus e raised to at minus t1 minus ts into e raised to at on minus I into a inverse v1 into vn. Okay, one more thing I forgot is we assume vn will be constant, so it is just a function of xn. It is just a function of xn and it is a function of t on. Rest all are constant. A is constant, t is constant, ts is constant. So it is a function of t on and it is a function of xn. Right? So this is known as my large signal discrete time model. So these are the analytical discrete time models which are there. Then what we do is we match this discrete time large signal model with the actual switch simulation. We have the switch simulation file which is in Simlink. We run that file, we get the data, what is the switch simulation plot. Then we run the discrete time model and for the same condition, for the same controller, again, everything. We run it for the same conditions and we get the discrete time values, the response for the discrete time large signal model, and then we superimpose it and we show that they match. That means the discrete time large signal model which I have derived from so much after checking each mode of operation from one state to the next state vector to the next state vector, etc. That is valid and is matching with the actual simulation which I'm doing in Simulink. Okay. So for doing that, I will use the plug and play power stage MATLAB model. Then I will use it in Simulink. I will do digital control with it. And I will validate the model using MATLAB transient simulation. I will do transient simulation. So what do we do is, see, how do we know that our closed loop control is working? In steady state, in a steady state operation, we can even run it open loop and it will work. It would work roughly properly. But when there is a disturbance, when there is a change, when it is the system is going from one steady state to the next steady state, that period is known as a transient. It is only in this time we know that it is able to reach the next steady state. Then the closed loop is working. Okay, so to verify that the closed loop operation is happening, we perform transient, low transient, input voltage transient, etc. on our model to verify that it is working. So this is the files. Okay. Last week I talked about how we can run the Simulink file using the MATLAB script. So this is very, very useful. So you don't need to keep on changing the values. You just store these variables and you run these files. Those variables get stored in your MATLAB workspace. And when you use these variables in your Simulink model, it will take the values of these variables and run the model. So it will simplify your time and you can just change as per your requirement. So this is my buck underscore parameter, which is the buck files, etc. All these are there. These are my controller parameters. We are using PID controller. We are using for digital voltage mode control. These are the two different load resistors are there. So why I'm having two different load resistors is because I want to apply a load transient. Okay. If I want to apply a load transient, then I require different values of resistors. Then also I will set the initial values of the inductor current, the capacitor voltage, etc. And then I will proceed. So then in this file, I'm also simulating it. I'm entering the values of Kp, Ki, Kd of the initial conditions, the parameters of the buck converter, and then I will simulate this simulink file, okay, by running this command. And the results of it, I will buck underscore result, which will store the data. That data, I will access it from here. I will access the time data, I will access the vector X data. So if you see, this is there are three data. One is, this is my inductor current, this is my capacitor voltage, this is my output voltage, this is my sampled voltage, this is my Vcon, this is my Vcon 1. So all this data is stored in X, and it is stored in form of columns. Okay, it is stored in the form of columns. Okay, these are the columns: 1, 2, 3, 4, 5, 6. So I'll have to access the data which is stored in this column. So this column consists the data of inductor current. That is why X dot dot comma 1. That means dot dot means I will store access all the data in all the columns. No, the data in all these rows, I will access the data, but for the first column. Similarly, the capacitor voltage is the data which is stored in all the rows, but for the second column. Similarly, the output voltage is the data stored in all the rows, but for the third column. That is how I will access the data. Okay, and then I will plot. There's a plot subroutine which will plot that data as per my requirement. Okay, it will plot the results. So these are the plotted results. This is how my inductor current is changing from one condition to another condition. That is, there's been a load step up. The load has been stepped up. The load requirement has been increased. So whenever there is a load step up, you'll observe that the output voltage falls. It will fall. And because of the closed loop which is working, the digital voltage mode control, there is a dip in the output voltage, but finally it is getting regulated back to its steady state regulated requirement of 1 volt. Okay. Because of the change in the load current, there's a dip in the output voltage, but it is being regulated back because of the closed loop current mode control. So the blue one which is showing is the actual analog voltage, output voltage is varying. And the red one which you see here, that is my sampled output voltage. Okay, so I'm taking one sample per cycle, and that is shown in this curve. So next, now what I will do is, I will run the Discrete-time large signal model. Okay, that was my Simulink file. Now I'm running the Discrete-time large signal model. I will use the same PID values, same resistors, same things, same values I will define. I will define the on matrix, off matrix, the B I will define, the output matrix I will define, and then I will run it. Okay, I will store these values and I will plot it. So to run it, I will require the dynamics of the model. What is the dynamics? How I will get the error voltage, then it passes to my PID integral, to my derivative, through my proportional value, then how this duty ratio changes, and how I will also have the duty ratio cannot be less than 0, it cannot be greater than 1. All these I will consider. Then I will use that for my large signal model. In that expression of the large signal model, I will apply it. And then I will see how the new state is changing from the first state to the final state. So all this is written in these plots of code, and then I will plot the results as well. So when I plot the results, what I see is these, you see these dots, these circles, okay? These circles are the discrete time model. What the discrete time model, doesn't show for the entire switching cycle. The discrete time model just captures the sample value at one instant within the switching cycle. So at this point where the sampling occurs, this point where the sampling occurs, this point again where the sampling occurs, it just captures those values and it stores that value. Okay, so this is the thing for the discrete-time large signal model. And this is for the inductor current, how it is also matching with the actual switch simulation. Now we will go to the small signal discrete-time model. So till here, any doubts are there? Please let me know. If there are no queries, I will proceed further. So Rajesh Reddy and Anis Mary B. So
We can proceed, sir.
we proceed, right? Okay. So I hope the previous things you're able to understand.
Yeah, we will get the. I have to
Go through it.
get those things one more time and then I will come back.
Okay. Okay. So if you have doubts, you can write down in the portal also, as well as on the YouTube video channel, so you can write. Yeah. So
Today the connection is also very intense with yours.
yeah, I
Yeah.
don't know why actually. This usually doesn't
Okay,
happen.
sir.
So I'll proceed. So this is my discrete-time large signal model. Okay? It is a function of xn and it is a function of t1. Now I want to find the small signal model. Okay, if I want to find the small signal model, SSM. Okay, I want to find the small signal model. What I will do, I have to perturb it. So what I will perturb it in terms of xn and perturb it in terms of t1. So my xn plus 1 perturb will be the partial derivative of this function with respect to xn into xn perturb plus df upon dt on and t1 perturb. Okay, this is like, the Taylor series and Jacobian, all these concepts, they use this formation perturbation. These can be done also using the plots and graphs, etc. But this is an analytical mathematical way, which is the standard procedure. So when I will find df dou f upon dou xn, what will I do? I am differentiating this. Okay, I'm differentiating this. Xn is only over here. Xn is not over here. So this entire term when I'm differentiating comes out to be 0. And when I differentiate this, xn becomes 1. So it becomes e raised to a into t. Okay. Now similarly, when I differentiate dou f and dou t on, I will get, I'll have to differentiate this and also I'll have to differentiate this. So when we do that, what we actually get is, let me not just write f in a better way. Now we write f. This term you ignore, this term you ignore. I'm just simplifying this term. I will write it as e raised to a t minus ts minus e raised to a t minus ts minus t on into a inverse v1 into vn. Now I will differentiate this term, okay? Because this term I'm ignoring right now because when I differentiate, it will automatically become 0. When I will differentiate this large term, this term will be 0 because it doesn't include t on. Only this term will come into the picture. So when I differentiate this, it becomes e raised to a t minus ts minus t on into minus of a, okay, minus of a into a inverse into v1 into vn. So this minus of minus becomes plus. This a and a inverse get cancelled. So dou f upon dou t on becomes equal to e raised to a t minus ts minus t on into b1 into vn, right? Any issues in this? So this is how I've done the derivative. Now I will write the total small signal model. So I will write it as my xn plus 1 per term is equal to e raised to a t xn per term plus e raised to a p minus ps minus p on into b1 into v in into t on per term. Okay, into t on per term. This is the equation I get. So what I will proceed with it further is, this is my control input. Okay, it is effectively u. This is my state. Okay, and this is like the sort of the derivative of the state. So when we do write in discrete time, we can write this as x per term n plus 1 is equal to a equivalent into xn per term plus b equivalent into t on per term. Okay, so when my a equivalent is equal to e raised to a t and my b equivalent is equal to e raised to a t minus ts minus t on into b1 into v in. All right, this is my equivalent A matrix, this is my equivalent B matrix because it is small signal. Small signal means it has become a linear model. Okay, I have made it a linear model. So I will get, so now if you see, this is a constant value. Okay, this also is a constant value. So the discrete time large signal model, I have linearized it using this Jacobian and this Taylor series, etc. And I have brought it into this form. Okay, so once I brought it into this form, then I can find a discrete time small signal models of this. Okay, discrete time small signal transfer functions of it. So any doubts still here?
No, sir.
Okay, so if you will remember now, A equivalent. Okay, one more thing is T on per term can be written as D into, can be written as D per term into T. Okay, because my T on is equal to D into, it is equal to D into T. D is my duty ratio. When I do T on per term, since my time period is fixed, only my duty ratio will change. So it is D per term into T. Is this substitution understood?
Yes, sir.
So just B equivalent will just change into e raised to a t minus ts minus dt into b1 into vn into t. Okay, what happens here? T also will come into the picture. So I've just written in the final expression. I will return it. Now I know A equivalent is given by this, B equivalent is given by this. Now I want to write in the form of a matrix. Okay, so this A equivalent, which is equal to e raised to at, I substitute it to be equal to I plus A into T. I is the identity matrix, so it just be 1 0 0 1, and A is what? Okay, it's not A. The A is 0 1 by C minus 1 by L and minus 1 by RC, minus 1 by L and minus 1 by RC into T. So T, when it goes, it gets multiplied by each and every term in the matrix. Okay, so it, when I add it, it will become 1 minus T by L, T by C, and 1 minus T upon RC. All right, this is my A equivalent. I have used an approximation of e raised to at. I approximate it to do I plus A into capital T.
That is the section.
This is till what about?
This is the series expansion, sir.
This is
I
series
plus
expansion.
80.
And the higher order terms I am ignoring. Okay. Yeah. So this is my A equivalent. And similarly, for the B equivalent also, this e raised to A, this also I can do the series expansion. And B1 is a matrix, Bn also is another, Bn and T are constant. So similarly, I can find the value of B equivalent. Okay. So using these methods, okay, you have any doubt? So using these methods, I can get the matrices. So let me just write the final. So A equivalent, we got already, I wrote it down. So B equivalent is V in T upon L and P minus TB V in T upon L C. Okay. When you do that expansion and multiplication of matrices, multiply by V in and P, you will get it to be of this one. Okay, this is my A equivalent matrix and B equivalent matrix I got. Now I want to find the transfer functions. If I want to find the transfer functions, what do I need to do is, these are my this my x n plus 1 is equal to, actually it is IL of n plus 1 and VC of n plus 1. IL of n plus 1 is my inductor current at n plus 1 instant, and VC of n plus 1 is the capacitor voltage at n plus 1 instant. Similarly, xn is the inductor current at the nth sampling instant, and VC is the capacitor voltage at the nth sampling instant. Okay. So this is my vector. Xn plus 1 is a vector because it consists of two states, IL and VC, and n denotes the instant. Okay. Now I want to find the transfer function. So what I will do, I know xn plus 1 per term is equal to A equivalent into xn per term plus B equivalent into this is D per term. Okay, D per term. So when I try to find the I take the Z transform of it, I will get Z into x per term of Z is equal to A equivalent into x per term of Z plus B equivalent into D per term of Z. So it will be Z I minus A equivalent into x per term of Z plus B equivalent into D per term of Z. Suppose I want to find the output voltage. Output voltage I want to find. Okay, V output n plus 1. That is related to my xn plus 1 given by this form C into xn plus 1. This is then control systems. Okay, this is the output matrix. Output matrix. All right, this is then control systems. So if I want to, yes.
V naught n plus 1 equal to. This
So
one comes from where, sir?
yes. So in the for buck converter, you have a capacitor is like this, and you have a resistor. Okay, and you have your inductor like this. Okay, this is my output voltage. So my output voltage is actually equal to VC in this scenario. Okay, in this case, because there is no ESR of the capacitor. If there's ESR of the capacitor, then there'll be the component of IL also will come into the picture. Okay. So in this case, in the ideal case, C will be equal to 0 and 1. Okay. So when C will be multiplied by xn plus 1, I will get V output of n plus 1. But in the actual case, it could be like some alpha RC, alpha, etc. Okay, in the actual one. But I'm doing the ideal case, so I'm considering C is 0, 1. Okay, so just assume that it is some C, which depends on whether I consider parasitics or I do not consider parasitics. All right. Yeah, okay. So now I want to find the transfer function, that is V output per term of Z with respect to the control input D per term of Z. So that will be equal to C into Zi minus A equivalent inverse into B equivalent into my U. U is okay, that is D per term. So this is my transfer function. Using this method, I can find the transfer function for the output, change in output voltage for a change in the duty ratio in the digital domain. See, we taught in the first slide, okay? The very first slide, I had shown this diagram. how GVD is there. Okay, depends on the duty ratio, how output voltage is changing. This is for the continuous time model. But now when we do for the discrete time, how we are finding it, I have shown it in the last line. All right. So if there are, so this is how we have done. So I will upload these things on the drive, and you can access this as well. And if you have any doubts, you can message me on YouTube as well. So I'll just briefly go through some questions, okay? Some questions which I prepared. Now this is zero order hole. Okay, zero order hole. That is G of S is 1, I derived it also, 1 minus e raised to minus st upon s. Okay. Now we want to find at the rate 10 radians per second and time is 1 second. So G of j omega will be 1 minus e raised to minus j omega t upon j omega. So you'll have to convert it to, you'll have to get it in terms of some magnitude and into some terms of some angle. Right? We'll have to use de Moivre's theorem, etc. And you can do this actually.
This e power minus j attracted cos j omega minus j.
Sorry, it is?
This e power minus j, we have to write it as cos j minus sin j.
Yeah. Cos.
And then
It is not cos j, it is e to the power minus j omega t. It is cos of omega t minus j of sine omega t. Okay. So that you have to substitute. Then you can, do the complex conjugate because j should not be the denominator, it should be the numerator. Okay, those things are standard mathematical tools which you can use. All right. So this you can try. Similarly, for this a boost converter, input voltage is 20 volt, output voltage 50 volt. So if that is the case, we know V output of Vn is equal to 1 upon 1 minus d. So this implies 1 minus d is equal to Vn upon V output. So d is equal to 1 minus Vn upon V output. That is equal to 1 minus 20 upon 50. That is equal to 0.6. Okay. My switching frequency is 100 kilohertz. So my time period is 10 microseconds. So the delay due to t delay due to dPWM is equal to d into t, that is 0.6 into 10 microseconds. So that comes out to be 6 microseconds. Okay, that is 6 microseconds. My delay due to my ADC is 100 nanoseconds. That I can write it to be 0.1 microsecond. So my total delay is 6 plus 0.1 is 6.1 microsecond. Okay. So
okay.
Similarly, now to arrange the steps to find the discrete-time small signal model. So what we did first is, if you remember, we first wrote the state space model, okay, for the various operating modes, when switch is on or switch is off. Then what we did is we found the state space solution from one operating mode to another, and then we determined the overall discrete-time large signal model. Then what we did is we perturbed that non-linear equation to find the linearized dynamics, and then we took the Z transform of that and from that corresponding equation to find the transfer functions. So this is the order in which we have proceeded. Okay. So yeah, so this is a very mathematically rigorous part. Okay, it will be a bit boring, but this is what will come in the exam, like these questions, like these concepts, etc. Because in the exam they cannot ask you to write if, like they can ask you to check FPGA code, Verilog code, etc. But they cannot ask you to implement it. Right. So such sort of questions also will come in the exam. So you'll have to prepare accordingly for it. So these things I will upload on a drive, and do you have any other queries?
Yes, sir.
Okay. Yeah. So yeah, this is very, very mathematical. Takes lots of time. But these are sort of questions which comes in the exam. Yeah. Okay, then. So then
Sir,
what
to understand this,
yes, yes, tell.
sir, to understand this, following the sir's lecture is sufficient, sir.
See, search lectures also are there. You can understand that. And so let's also refer to certain papers. Yeah, research papers. So you could refer to that as well. See, this is basically control systems, right?
Yeah. Yes.
So there's a new concept which you have not been taught in control systems earlier, the discrete time model. So the discrete time model has to be is a bit new. It's a bit new how we are going from one, like how are we going from one state to another state. Yeah. That is a bit new. Okay, this is a bit new. It's a new concept, etc. Then you can just derive it. You can derive it from one thing, and you can work with that. That is for the discrete time model. And how are we getting the transfer function? So the transfer function is very important. First, we analyze the system and we verify the operation of the system based on a transfer function model which we have made. And because we are making the transfer function model and we are designing our controller and analyzing our operation based on those models, we want those models to be accurate. So for that, we are studying the continuous time model and the discrete time model. Both we are considering. So one main factor which I forgot to mention here is the continuous time model with the delay. That it represents very closely the actual discrete time small signal model. So to make the discrete time small signal model, it takes so much of time. It is so tedious. But the continuous time model, small signal model is quite easy. But just you have to incorporate the delay due to the digital pulse width modulator and the ADC delay.
Okay. Okay, sir.
Okay, so Kanit Das, do you have any doubts? I'll actually share this one, the links to the YouTube channel as well as to the drive folder where you can access the lectures. So did you get those links now?
Yes, sir.
So you can refer to that.